you can form a color signature bound state. Okay, so this is a very unique prediction of QCD. There's no such analogy in QED because photon has no self-coupling, so you cannot form a bound state like a photoball. Okay. Now this plot shows the spectrum, glueball spectrum, calculated in the quintillaris QCD approximation. Okay. As you can see, that it's calculated by contact group. As you can see, the lightest glueball has a mass about 1710 MeV. Okay. And the next last one is the tensor glueball has a mass of 2390 MeV. And the next one is the pseudoscalar glueball with a mass of 2560 MeV. Okay. I just mentioned that those calculations was done in the quinch large QCD, so you don't have a 4 degrees freedom in the calculation. Now what happens if you do the calculation in the full QCD, where you have to consider the 4 degrees of freedom? So you have to ask the question. As a consequence of the Q Now, in practice, it's very difficult to identify or to search for the glueball. But nevertheless, a glueball state must show the following, must satisfy the following features. First of all, it must be produced obviously radial jet side decay. Because the jet side decay to the photon to gluon can be calculated very reliably in the framework of the QCD. Okay. And the glueball will come somebody to the color signature like gluon state. Okay. And also it must be suppressed in the gamma-gamma reaction because the glueball doesn't have a charge, doesn't carry charge. So it will not come to the photon directly. It may be will come to photon maybe through the loop effects. Okay. And also you will expect that the decay width of the glueball is quite narrow. Which can be argued for the Largian approximation. In the Largian limit, the glueball decay width was proportional to the 1 over nc squared, whereas the cubic bar state is proportional to 1 over nc. Now, normally, because the glueball is a flavor singlet, so you expect that the decay pattern will respect the flavor band. Okay, it's a flavor band. Okay, but in the two-body decays, we see that actually color suppression effect is important. Okay, and which I will go to address later on. So let me first of all focus on the scalar glueball. Now, in nature, there exist two different nanonates for the scalar methods. Okay, one nanate with the mass less than 1 GeV, the other nanate with the mass above 1 GeV. The lighter nanate is made of consists of the sigma, kappa, F0 980, F0 980. It is widely believed that the light nanate is made of 4 quarks. By contrast, the heavy nanate with a mass above 1 GeV usually is believed to be made of 2 quarks. Okay. Now, in the quantum model, there's only you can only have 2 isosceles scale method. Okay. But experimentally we have 3. F0 1370, F0 1500, and also F0 1710. Okay. So we have one more isosceles state than you will expect from the quantum model. So this means that one of them should be primarily a glueball. In other words, glueball is hidden somewhere there. Okay. So So couple model just can only accommodate to isosymmetry state. Okay. Now F0 3070 and F0 1500 will decay mostly to 2 pion and 4 pions, whereas F0 1710 will decay mainly into the KK bar. So you will expect that the F0 1370 and F0 1500 are N bar state. N bar is the right state here. U bar plus D bar. Okay. And the SS bar state for the F0 1710. Okay. Now in 1995, Amsterdam and Frank Cross claimed that the F0 1500 is covered at the Leo as evidence of for the scalar glueball, because it is decayed to the pi or KK bar, eta or eta prime. It's not compatible with a simple KK bar picture. Now a few years later, Amsterdam made a more concrete argument, okay, against the KK bar integration. The argument goes as follows. Let's write the F0 1500 in terms of N bar state coponia and S bar coponia in terms of the missing alpha, cosine alpha. Okay. Now let's write the decay rate of the F0 to the two photons. Okay. So this coefficient is the charge of the N bar coponia, and this one organized is a charge square of the SS bar. Okay. Now, the experimental answer are observation of the F0 1500 in the gamma reaction will requires that the alpha is close to the 75 degrees, and hence it will imply that the F0 1500 is dominated by SS bar. But we just argued before that the F0 1500 is N bar dominant. Okay, so just a conflict is between each and is one. Okay, so let's reason why Amsterdam and Frank Cross argue that F0 1500 is not a KQ bar state. Instead, it is Google dominated state. In fact, in the earlier lattice calculation shows that the lattice calculation that it shows that the global mass is close to 1550 MeV. Okay, so as a consequence, you can argue that the F0 1500 is dominated by scalar global. F0 1710 is because the pi is suppressed relative to KK bar in the decay of the F0 1710. So it's a primarily SS bar state. And for the F0 1370, KK bar is suppressed relative to pi. So it is dominated by N bar state. So one can write down this mass matrix in the global SS bar coponia and the N bar coponia state. Okay, so it is the mass. Ng is the mass of the global, Ms the mass for the SS bar coponia, and then likewise bar. Why is the mixing between the global and the coponia? Okay, so one can fit this mass matrix to the major mass of the scale meson, and to the branch ratio of the Swanton scale of the mesons. So by the end of the day, you find out that the F0 1710 actually is dominated by SS bar, and the F0 1500 is governed by the global. Okay, and after 1370 is mainly dominated by the N bar state. Okay, in this model, the premise is FG. The mass of the Bayer global is about 1500 MeV. Okay, and NS bar, the mass of the SS bar coponia is larger than the global and larger than N bar. In fact, the mass difference of the SS bar and N bar coponia is about 200 to 300 MeV. However, just lot of problems with this model. But first of all, experimentally, we know that the A0 1450 and the K0 star 1430, the mass are almost the same, even though this guy has a strange quark inside. Okay, so if the mass difference between the SS bar and the N bar coponia is 200 to 300 MeV, then you cannot explain the degeneracy the near degeneracy of the NO 1450 and also KGO star. Now, suddenly, if NO is if NO 1710 is SS bar dominant, then because phi meson is made of SS bar, so you expect the decay rate of the radial jet side decay to the NO 1710 accompanied by the phi meson will be larger than the decay rate of the to the NO 1710 accompanied by omega meson, because omega is made of UU bar DD bar. Okay, but experimentally it's the other way around. The base has measured the decay rate of the two different decay modes. In fact, it's the other way around. Omega F naught is larger than S1. Okay. Also, I just mentioned before that the radial jet side decay, you expect that if it is a glueball, then we come strongly to the digluons. So if MNO 1500 is primarily a glueball, then it should be seeing the rich radial jet side decay. So that you expect that the decay, the radial jet side decay to the FNO 1500 should be much larger than the FNO 1710. Okay. Again, the opposite is true. The best measurement shows that actually this guy is almost larger than the decay rate for the FNO 1500 by 1 order the magnitude. And also, if NO 1500 is composed of many of the glueball, you expect that the ratio of the branching fraction of the pi over k bar is about 3/4 if the company is a Fraser band, because it's just a 3 pion state and the 4 possible k bar state. So the ratio is 3/4. But actually, the ratio is actually even smaller than 3/4 if you consider the effect of the calibration, which I'm going to mention later on. Okay, but experimentally, the ratio actually is 4.1. Okay, so much larger than what you expect from here. If FNO 1500 is a glueball. Okay. The last thing is just attention with lattice QCD calculation. In fact, I mentioned before that in the lattice QCD calculation, first of all, in the Quincy lattice, there's several Quincy lattice calculation. The first one was done by Morningstar Hilden, 1998. They got the 1750, and also later on the Lee Weingarten got this number, and later on the Kentucky group got this number. Okay, but those calculations are done in the Quincy approximation. You don't consider the dynamic Fermi effects. Okay, the first full QCD calculation was actually this year just a full QCD calculation done by UK QCD. Okay, and in here the glueball is not pure glueball. It will mix together with the quarks. Okay, but nevertheless it shows that the scalar glueball mass actually is not significantly affected by the quark degree field, not by the dynamical fermions. Okay, so the bottom line is in the mass of the scalar glueball before mixing is overall 1700 MeV rather than 1500 MeV. Okay. There's also just many other scenarios. For example, like Lee Weingarten, they also perform a lattice calculation. It shows that suggests that the FNO 1710 is a promising candidate of the glueball. Okay, and the FNO 1500 is bar dominant, and 770 is governed by the NMR state. In this paper, they also show that argue that the FNO 1710 is the glueball, but the mass difference is a little bit high, quite high. Okay. In this paper, they also consider, based on the color advantage, they found out the whole possible solution, and the one solution is FNO 1710 is a glueball. So the upshot is there's a hard debate as to which state FNO 1500 or FNO 1710 is a candidate of the glueball. Okay, there's a hard debate. But if you look at the PDG of the 2006 version, it says experimental evidence is mounting that FNO 1500 has considerable affinity for groove, and later the FNO 1770 and the FNO 1710 have a large UU bar plus DE bar and the SS bar components respectively. So it seems that according to PDT, the debate is it's gone. There's no such debate because according to PDG, the glueball is definitely is not 1500 MeV. Okay, and the core content of those two states have been fixed. Okay, but actually it's not quite true. So in fact, the tone of the PDG has been changed since 2008. Now PDG says that the ethanol 1500 or alternatively the ethanol 1710 have been proposed as a candidates for the scalar group. So even according to the PDG, yes, this is really a debate. Okay. Now, a couple years ago, my collaborator, Kobe Liu of Kentucky, Jim Chen Choi in Taiwan, and we try to study this issue. Okay. And our study is quite simple. We just need to use two simple and robust input. Okay. Those inputs are very simple and very robust. First of all, we made an observation that to the first approximation, SU3 symmetry actually is quite good in the scalar meson sector about 1 GeV. The reason is the following. You look at those scalar meson A norm 1450 and the KGO star 1430. Also in the Chang meson sector, we have a D0 star 2308, also DSS star 2317. Although the second guy, this guy, carries strange form. Nevertheless, you see just almost a mass degeneracy. Okay, so in other words, for the scalar meson sector about 1 GeV, the mass of the coponia, the mass for the SS bar coponia should be very close to the mass of the NA bar coponia. Okay, in fact, this feature has been confirmed by large QCD. Okay, the Kentucky group has calculated the mass of the scalar meson A0 and also the actual scalar meson A1 as a function of the quark mass or as a function of the n pi square. Okay, and then you see that for the mass, for the quark mass is below the strange quark mass. The mass of the A0 remains almost flat, remains constant, while the mass of the actual scalar meson will decrease until here. Okay, so in other words, the mass for the scalar meson A0 or D50, the mass is independent of the quark mass, or the quark mass is below the strange quark mass. So in other words, SU3 symmetry apparently is a good one for the scalar meson sector. Okay. So in other words, SU3 symmetry has been also confirmed by the large QCD. And according to the large QCD calculation, the predicted mass for the KGO 1430 is about 1.41, and it's 1.42 for the HF star, or actually it's a small star here. So the near degeneracy of the KGO star and the A0 has been confirmed by the largest QCD. So each feature is quite unusual because it's difficult to understand why there's such a near degeneracy in the quark model. And as far as I know, nobody is able to explain this near degeneracy within the framework of the traditional quark model. Okay. The second input we have is we learned from the Quinn-Gillard's calculation. The glueball mass before mixing is about 1700. So I use two simple input. This is an empirical one. Also, this is a large calculation told us that the mass must be close to 1700. So we just use two simple study point. Okay. So let's consider the mass matrix. Okay. So this is the mass for the coponia and also glueball. Okay. Plus some mixing. And the X here is the quark anti-quark annihilation. Okay. And the Y stands for the glueball anti-coponia mixing. Okay. The superscript X means possible SU3 breaking effects. Now I just mentioned before that based on our first input, we can treat SU3 symmetry as a good symmetry to the first approximation. So I will under SU3 symmetry I can as a MUD, NUD, and as a bar. Okay. So first of all, the mass matrix B can be decomposed in terms of two by two mass matrix. Okay, within the basis, isofactor, NO, octet, and singlet state. Okay, so it's a complicated mass matrix can be reduced to a two simple 2 by 2 mass matrix M. Okay, so the eigenstate of the first 2 by 2 matrix just is nothing but just an isofactor NO. Okay, the mass is well measured, is 1474 MeV, and the other eigenstate should be NO 1500 because it's mass. So in the SU3 limit, you expect NO 1500 MeV should be have a mass like 1474. It's same as the NO. Okay, so this is the in the SU3 limit, NO 1500 just an octet state. Okay. Now the eigenstate of the is a mass matrix should be NO 1370 and also the NO 1710. Okay. Now, if I turn off the mixing between the glueball and the coconia, then one of the state must be NO 1710. The other state must be NO 1370. So use the circle input before here. So rely on the circle input. Then I know that. Then we know that when we turn off the Y, the eigenstate, the heavy one must be the NO 17. So the SU3 when you turn off the mixing, NO 17 must be a pure glueball. And the NO 1370 is a pure SU3 singlet with a mass n plus 3x. So from here we can fix the parameter x small x. Okay. Now the next step we just turn on the mixing between the glueball and the coconia. Okay, turn off the Y. Okay. And then if Y is about same of the order and magnitude as x, then the mass shift the mass correction to the 1317 and 1710 would be quite minor. It's about only at the most about 10 MeV. So anyway, in SU3 limit, the mass of the bare glueball is close to 1700 MeV. So the next question is, if NO 1710 is composed of many of the glueball, then how do we understand its decay pattern to the two pseudoscalar methods? Because because the glueball is a flat singlet, so you expect that the copy is a flat blind. And so the ratio to the pi of the KK bar, you expect it is 3/4, as I mentioned before, because it's just 3 possible pi state and 4 possible KK bar state. Okay. Taking into account the phase space correction, you expect the ratio is 0.91. But experimentally, the ratio is not well measured. Okay, it ranges from like number smaller than 0.13 and close to 20, 0.32, and also 0.41. Okay, so it's not well measured. Anyway, this number is adopted by PDG. Okay. No, so the question is why the ratio is smaller? It's smaller than 1/2. Okay. Well, actually, it was found out a long time ago by Carson and also by Conwell, Sony, and later on by Chenoweth. That because of the conservation of the angular momentum, actually glueball, scalar glueball or pseudoscalar cannot decay into the QQ bar in the color limit. Okay. In fact, you can figure out through the conservation of the angular momentum. Okay. So the next question is the color suppression at the pop level will manifest at the atom level in the same way. So if this argument is correct, then we expect that the ratio to the pi over KK bar is proportional to NU and Q squared over NS squared. But we know that the stretch pole mass is There's one order magnitude larger than the light out of the box. So the ratio here is of order like 10 to the minus 2. Okay, of course it's too small compared to this one. So this means that the current separation at the hadron level is not so strong as that in the Hawking level. Okay. In fact, there are several papers. For example, in each paper, the operator NQ should be interpreted as a characteristic rate like a scale of the constituent force. Okay. And in each paper, they argue that the instantaneous effects will lead the so-called color separation. Nevertheless, just one large calculation done by Weingart a long time ago. Okay, they show that the ratio of the G to the glueball coupling to the pi to kk and to eta as is the ratio. Okay, and you can see that the alpha is quite large. Okay, nevertheless, it shows just a color separation effect. Okay. So what we have done is we just fit the model, fit the mass measure I mentioned before to the ratio of the branching fraction. Okay, there's a mass here, there's a ratio of the branching fraction. Okay. Now, first of all, we assume that there's no color separation. In other words, the coupling of the glueball to the pi is the same as kk and eta. We found out the predicted decay width of the F0 17K is too small. It's less than 1 MeV. And we know the total decay width of the F0 17K is about 135 MeV. Okay. So in other words, the predicted decay width is just too small compared to this band 1. Okay. So the next we consider two different cases of color separation. Okay. In the first case, we consider the ratio is like 1.1 to 1.6 to 1.59. Okay. The second one has a large color separation rate. Those two numbers we choose according to the largest calculation here. Okay. So the number I show here are in the range of the largest calculation. Okay. It turns out the scenario 2 is much better because scenario 2 gives a better ratio for the like S1, gives a better the decay width like for the F0 1370. Okay. So the punchline is we found out that the scenario 2 where the color separation is a huge is more favored. Okay. So by the end of the day, we found out in our model that the F0 1710 is dominated by glueball, okay. So it's primarily a glueball, and the F0 1500 is basically SU3 octet because octet cannot have mix. Cannot have a mixture with SU3 singly the glueball. So the mixing with the glueball is quite small, only 0.03. Okay. And the F0 1717 is basically a SU3 singly, but because it's a SU3 singly, so you can have mixing with the glueball. So the glueball content for the F0 1370 actually is not small. Okay, it's about 30%. And so our wave function for those isosceles state actually is quite opposite to what you have in the Epsilon-Frank-Cross model. Okay. In fact, it can be illustrated by this cartoon. Okay. So in our model, the F0 1710 is dominated by the green one, which is glueball. In the Frank-Cross model, F0 1710 is dominated by the red part, which is SS part. Okay. So in our model, the parameters for the N bar and the S bar four-cornea is given by here, and the mass for the glueball. So you see that the hierarchy is NG glueball mass is larger than S bar four-cornea and larger than the N bar four-cornea. Now, because the mass difference is only 25 MeV between the SS bar and N bar four-cornea, so we are able to understand the near degeneracy of the N0 1450 and also Casio star and also N0 1500. So there's no problem. Also, because the N bar content is in sky F01710 is more than the excess bulk component. So you expect the jet side decay to the F01710 accompanied by omega mesons larger than the phi meson. Like we say, confirmed by the experimentally. And also because F01710 is primarily a glueball, so you expect it has a large rate in the radial jet side decay, and also is consistent with the experimental measurement. In fact, the radial jet side decay is one of the best places to test the scale glueball. Okay, just one largest calculation recently by the I had group in China. Okay, they calculate the branch rate of jet side to the scale glueball, and the branching fraction is about 4 times 10 to the minus 3. Okay, but this is what's done with the pinch approximation. Okay. Also, you can look at the best measurement of the radial jet side decay for the F01500 and the decay to pi subsequently. Okay. From here, actually, you can use the branching ratio of the F01500 to pi to determine the branching fraction of jet side to the F01500. It's about 3 times 10 to the minus 4. And likewise, there's some measurement of the jet side decay, radial jet side to the F01710. So the branching fraction of the 1710 to kk bar or pi, I mentioned before, it's not well measured. Nevertheless, you can use the central value, and you can figure out that the branching fraction for the jet side to the F01710 is about 2 or 3 times 10 to the minus 3. So it's one order of magnitude larger than the F01500. Okay. Also, you can look at the low bound. Okay. From here, you measure the gamma pi, gamma eta. Okay. The low bound is like 1 times 10 to the minus 4. Now, for the F01710, you see the low bound. When you sum over those states, the low bound is about 1.8 times 10 to the minus 3. So even from the information of the low bound, you can figure out the decay rate for the 1710. It's almost one order of magnitude larger than the F01500. So this is a clear indication that F01500 cannot be a promising candidate for the glueball. So from our point of view, it's quite important to revisit and check the color separation effect, because the previous large calculation was done 17 years ago. Okay, and during past 17 years, just no any renewed calculation for the color separation effect. Okay, the error bar is quite large in the previous calculation, so it's quite important to have a new improved calculation for the color separation effect. In fact, if the color separation effect is confirmed by large CE, then we'll rule out the F01500 or sigma 600 as a possible candidates for the scale glueballs, because the ratio to the pi over kk, you expect experimentally is 4. Okay, and if the F01500 is a glueball, you expect that the actual ratio is like 3/4 or even less. Okay. And sigma cannot be a candidate of the glueball because the decay width is too large. So about 600 to even 100, 1000 MeV, so it's quite broad. Okay. Okay, each table just summarize what I said before. Okay, item by item. Okay, so I will not bother to read all and we can take a look. Okay, I will skip this one. Just a warning here. There's 2 new isosceles scalar mesons observed by Bass in 2004 and 2006. Okay. In the jet side decay to the 5 pi, Bass observed a new isosceles state, so-called F01790. Okay. It's constructed mainly in the pion decay modes. Okay. Unlike the F01710, it's mainly constructed from the kk bar state. Okay. Also, just another new state is called X18 curve. Okay, and it has been confirmed by Bass recently. Okay, the mass is about 1795, so it's very close. So you may ask, should we consider the mixing of the glueball with those 2 states? in principle, you have to consider the mixing with those two possible new isosceles states. Okay, the marks are very close. Okay. In fact, 7 years ago, about 2006, people suggested maybe those two states are state. So if you use AN bar coponium, SS bar coponium, and glueball to construct different isosceles states, then they suggest that maybe the ethno-17 plane is GNN, is a hybrid state of the glueball with AN bar, and the ethno-X1812 is made of the gluon SS bar. Okay. Anyway, it's a conjecture. And so each issue remains to be investigated because in principle, your glueball you must have a mixing with those two new isosceles states. Okay, let me switch gear to the pseudoscalar glueballs. In 1980, Mark II observed a new resonance in the radial jet side decay. Okay. And the mass is about 1.4 per GeV. And initially, Mark II identified state with E1420. It's first discovered by the at the CERN in the PV bar in the proton regions in 1983. Okay. E stands for Europe. Okay. Because it's the first particle discovered at the CERN. Okay. Now, later on, people realize actually the resonance discovered by the Mark II is not E1420 because its state is actual vector meson, and it's known as F1 1420. Okay. So anyway, its resonance has been renamed iota, or just the font is not right here. The iota, okay, 1440 by Christopher and also by Mark II. Okay. So, shortly after the discovery of this new resonance, many theories like Donahue, Johnson, Chenoweth, they suggest to propose that iota is the candidate of the pseudoscalar glueball. Okay. In 2005, a new resonance, so-called X1835, has been found by the base group in the jet side to the gamma, eta 1. Okay. And was confirmed by base 3 recently. Okay. In 2006, in 2006, many theories suggest that this is a possible candidate for the pseudoscalar glueball. And last year, base 3 also discovered another two neutral state, isosceles state, X2120 and also X2370. Okay. Now, in the community, it's widely believed that the iota 1440, which is renamed eta 1405 by PDG, is a strong candidate for the pseudoscalar glueball for two reasons. First of all, the branch fraction of this radial jet side decay to the iota is about the 10⁻3. Okay, it's much larger than what you expect for the measurement of the radiation of the eta 1295 or eta 2225 in the radial jet side decay. Also, in the gamma reactions, the iota was not seen. Okay, but the eta 1475 has been observed in the K-pi final state gamma reaction. Just one excellent experimental review article published in this journal. Now, the interpretation of the pseudoscalar glueball of the iota also is supported by the theoretical model, so-called fractal tubular model. Okay, it's proposed by Bradiev. Okay. But the trouble is, iota is not favored by most of the other calculations. In the largest calculation, in the quintilargest calculation, we know that the mass of the pseudoscalar is about 1.6 GeV. Okay. There's also 2C calculation. shows that the mass of the pseudoscalar glueball should be larger than 1.8 GeV. Okay. There's also quark model calculation. So the mass is lies in the range. Okay. So anyway, all the other means like lattice period, QCD stand rule, or quark model shows that pseudoscalar is the heavy than the tensor glueball and the heavy than the scalar glueball. 3 years ago, my collaborator Hervé Liu and also my colleague Xiangnali, we try to study this issue. Okay, so we consider the mixing of the eta prime. Okay, normally the mixing of the eta prime was
so in this parameterization, you only have two unknown. You just only have one unknown mean angle, phi g, the mean angle between the glueball and the eta 1. Okay, and then you can define the decay constant for the physical eta prime and glueball, and also for the quark flavor state eta q, eta s, and the bare glueball state. Okay, so you just define those decay constant. Okay, sorry. So you can relate the decay constant of those physical state to the decay constant of those quark flavor state and the bare glueball through this relation. So the mean angle here is the same as the one you have here for the wave function. Okay. So then you apply the so-called equation of motion, and you got some equations. So you can get the 6 equations from the equation motion. Okay. And so you have a lot of unknown inputs. Okay, like eta QQ, eta SS bar. You have like eta Q glueball and eta Q glue, and then there are also other terms. Okay. Anyway, so we have 6 equations, but we have so many unknowns. Okay, so in order to make a progress, we have to rely on some approach, and so we use the Toulouse lodging approach. So in the lodging limit, those are decay constant, the mass of the glueballs and the quarks, and also the matrix element of the GG tilde. Okay, scale in this way. Okay. So what we have done is we first of all consider the larger limit, the leading order in the 1/NC expansion. Okay, and so we keep those terms which are there in the larger limit. We neglect those terms which are subleading in the 1/NC expansion. Okay, so we keep those diagonal mass term and neglect the other mass term which can be neglected in the next leading Lagrange expansion. Okay, so we found out just from the ratio of the last 2 equations, from the ratio of the east equation and the east one, we can ignore the mass term here. Okay, in the Lagrange limit. So consider the ratio of east one over east one, and also the right hand side term here. We got this equation. Okay. And when we first obtain this equation, we are extremely excited. Why? Because in this equation, there's only one unknown. It's the mass of the glueball. And for the other parameters, like decay constant of the Fs over Fq, or the mean angle of the glueball mean angle, it can be measured from the Crow analysis. Okay, so Crow has analyzed the experimental data of the radial phi decay to the eta prime and to eta. So Crow has measured the mean angle of the glueball inside the eta prime with to be 20 degrees. In fact, this equation shows that it's very insensitive to the mean angle of the phi g, because you have 1 minus cosine phi, so it's proportional to phi g square if phi g is small. Okay, so it's insensitive to the precise angle, glueball mean angles here. Okay, so That's the reason why we are so excited, because in this equation, all the other parameters are known. Okay, so for the first time, we can determine the mass of the pseudoscalar group from this equation in the large n approximation. Okay, and a priori, we don't know what's the mass of the group. It can be as light as iota, which is 1440 MeV, or it can be as heavy as like 1.6 GeV, as suggested by large QCD. Okay, so when we plug in the number of those one into this equation, the result we got is S1. So hallelujah, this is precisely the mass of the iota 1440. So we suggest that the iota is a promising candidate for the pseudoscalar group. And then we check whether or not its result is stable, because you have to check the OGI correction. You have to check the subleading Y/NC correction. So our conclusion is that the analysis is very lengthy, but our conclusion, our bottom line is the group mass is about 1.4 GeV. So this is precisely iota. Okay. Then people ask us that how do you explain that your calculation is not compatible with the largest QCD? The largest QCD told us that the mass should be like 1.6 GeV. Okay. But we don't have to worry too much, because a lot of calculations are still done in the quintuple approximation. And it has been noticed by the gentleman that the mass of glueball in the full QCD with the diametrical fermions could be substantially lower than that you expect in the quintuple approximation. So this gentleman obtained this equation. So anyway, we conjecturate that the pseudoscalar group could lie at a lower mass than what we predict in the from lattice calculation because of the dynamical fermion or axial anomaly effect. In fact, we know that in QCD, just one famous so-called U1 problem. So in QCD, based on Kähler-Lagrange symmetry, you expect that the eta prime is as light as a pi. And this is a very famous so-called U1 problem. Now, once you consider dynamical fermion effect, once you consider anomaly, the anomaly or incident effect will lift the eta prime to as heavy as like 958 MeV. So it's possible that the dynamical fermion effect plays the same role here. In fact, the so-called topological susceptibility defined in here is about 10 to the minus 3 GeV force in the quintuple approximation, in the quintuple lattice calculation. But it is very small. In fact, it vanishes in color libre in full QCD. In the full QCD, it's about 10 to the minus 5. So it's quite conceivable that in full QCD, just a very sizable dynamical fermion effect on the glueball, on the pseudoscalar, as it does on the eta and the eta prime before. Okay. So now, nonetheless, I can summarize in this way that the present situation for the pseudoscalar glueball actually is quite murky. Okay, because I just mentioned before that we believe the iota 1440, eta or iota or eta, okay, 1405 is a promising candidate for pseudoscalar, but its mass is a substantial exponent what you expect in the quintuple lattice calculation. Okay. Just some other neutral isosinglet state like X1835, X2120, or X2370. In fact, many people, some also prefer to consider its state because it is close to the what we expect from the quintuple lattice calculation. Okay. Okay, summary. From the relative shape side decay and also from the major ratio of the pi over kk production, and also from the near degeneracy of the A0 1450 and the K0 star, imply that the F0 1710 is primarily a lattice scale glueball. And our analysis of the eta prime and glueball mixing shows that the mass of the pseudoscalar ball is about 1.4 GeV. And which suggests that eta for 1405 or iota 1440 is a promising candidate for the pseudoscalar glueball. But it is lighter than what you expect in the quench lattice result. So a full lattice calculation is definitely urgently needed. Thank you.
If there are any questions from the audience, I hope there are. Please.
You talked about the contribution to the pseudoscalar making the eta prime heavier, right? The pseudoscalar glue ball. What about phi? The phi meson? Will they be?
In fact, the meson phi?
Yeah, the meson phi. Yeah.
It's still
So it will
1 equals to 1 GeV.
So
it's not affected by the dynamic Fermi effect. It's
So
not affected by anomaly.
So you think that there's
It's a
substantially
typical meson. It's quite normal.
yeah. So you will have substantially different behavior of eta prime and phi because of the glue ball admixture. Have I understood this correctly?
Could you repeat again?
Eta prime
Yes.
has a contribution because of pseudoscalar glue ball,
Yes.
but phi will be clean.
Yes.
So that means substantially the behavior of these two singlets will be different because of the additional glue ball complication in eta prime?
Yes.
Okay.
Yes.
You discussed scalar and pseudoscalar glue balls.
Yes.
So what about the tensor glue ball? Don't you expect there the mixing will be small because the QQ bar ground states will not contribute to?
There's a candidate so-called 2.2 GeV, and most people in the literature, most people believe that the guy is
They are pure.
is a tensor global. Yes, 2.2. It is precisely what you predict in the quench lattice.
So the problem is only with pseudoscalar and
especially for the pseudoscalar global. This guy is really
yeah.
because of the anomaly effect. And so it is status is quite unclear. Although we propose that iota is still a strong candidate. Yeah.
So I was curious if this, once you put in this eta prime G mixing angle, whether, you know, I mean, at some point, I don't even know if now it's still there, but the B to eta prime modes had very large branching ratios, B to eta prime, K eta prime, and I think pi eta prime. And will those be, I mean, if we put in these mixing angles, would that data be consistent? I was curious whether you have looked at that.
Okay, let me repeat your question.
Yeah.
So your question is like in B decay to the K eta prime, it has a largest branching ratio in the two-bar decays of the B meson. Okay, in fact, in the early days, people they think about many different possibilities. They try to pursue a different possibility. And one of the possibilities, people suggest that maybe eta prime has a large or chunk content, or maybe some glue content. Try to expand. But nowadays we know that, like in the framework, so-called QC localization, one can understand the branching ratio of the key eta prime not only quantitatively, also qualitatively in terms of the interference of the two different penguin background contribution. So the number can be understood in the framework of the QC localization. So apparently just no need for such
Just remember that when it was measured, it was very, you know, it was very unexpected, and so that's why what I.
But even if you take into account, I think the contribution is still substantially small compared to the major penguin contribution.
I have one short second question, and that is about the F0 1710 decays. So individually, if I understand, maybe I missed it, the branching fraction just for F0 1710 to KK bar and to pi pi are not individually known, you only know ratios. Is that the correct statement? If the F0 1710
F0 1710 to the pi pi over KK?
to KK bar and pi are
Pi.
individually experimentally measured, or you have
Oh, well,
ratios?
okay, I cannot. Can we come back? Could you?
Only the ratios are known. You don't individually know the branching fraction for F0 to pi or F0 to kk. Well,
Yeah, yes.
Just want to point out there's another way of looking for these things or the absence of these things. If you take a B sub s to k into charmonium, like let's say B sub s to j psi, then you're left with an isoscalar system, which is SS bar. And it's already been published what happens when that goes to pi. And there will be a publication out of what happens when that goes to kk in a few months. And you would not expect glueballs to appear there, for example. And it also gives you the ratio of these branching fractions of the various sides.
Thank you. Actually, I read your paper. Yeah.
Sir, you talked about the scalar glueball and the pseudoscalar glueball. So the glueball is a bound state of all the 8 gluons. Now, how do you distinguish in terms of the components of these gluons between the scalar glueball and the pseudoscalar glueball?
Well, the phenomenon is
how do they are different in the combination of the gluons? Or it is not?
okay. In my talk, I didn't specify how many gluons inside the glueball. Okay, can be 2, 3, okay. But in early days, people try to use the so-called constituent gluon model. Okay, so a constituent, just like a constituent quark, the mass it could be 350 MeV for the uptown and 500 MeV for the strange quark. Okay, and so in the so-called constituent gluon model, the mass is about 500 MeV. Okay, but based on this model, in order to have a pseudoscalar glueball, you must have three gluons inside the glueball, because it's a pseudoscalar, so the parity is odd. Okay, so in order to get odd parity, you must have 3 gluons. Okay, but in this talk, I didn't specify what's the number of the gluons inside the glueball.
So it is not always the combination of 8 gluons. In pseudoscalar, you have 3 gluons, and in scalar, you have 2 gluon bound state.
Well, for scalar glueball, you can have just 2. Yeah.
Only even number each.
In your very early slides, you mentioned about the glueball state will mix with QQ bar state to destroy the glueball state, right? So I just want to understand, say a glueball consists of 2 gluons only. So it's a color singlet state of 2 SU3 adjoints. And so why it's so favorable to mix with a QQ bar, which is again a color singlet of 2 SU3 fundamentals? So why it's such a favorable process?
What is that?
The coupling is large. So QQ bar going to gluon is a very favorable process.
Yes, no, but it was mentioned about mixing, not decay kind of.
No. If QQ bar goes to gluon, goes back to QQ bar. That's the process. That causes this.
It's through the annihilation diagram, like a QQ bar annihilation diagram. You can have 2 gluons, okay, then coupled to the glueball.
No more questions. Let's thank the speaker once more.